Hello everyone, we are the BYTE team and we are going to present in this video our final challenge of Cyber Physical Systems 1. First of all, welcome to our class break presentation. It's for me an honor to present our final challenge solution. Today, we will delve into the fascinating world of robotics and automation as we explore our solution to the final challenge using a mobile robot with an integrated arm. Our challenge was to create an automation program capable of transferring an object from one location to another and return it to the starting position with a controller in the velocity of our mobile robot and integrate a routine in the integrated arm, demonstrating the principles of an automation and robotics and create a real-life simulation of the real-world industry problems. Our team consists of 3 mechatronic engineers and 1 mechanic engineer. Each member contributes to different aspects of the project, such as the fixtures design, uses in the simulation, math modelation, simulations in general, debugging, physical experimentation, and other tasks. All of these tasks were developed with the solution strategy of the waterfall.
How the program works. Our control system utilizes data from the odometry of the robot to estimate the position of the robot, calculating the error, taking into account the set point and the current position of the robot returned from the robot's odometry. The robot's path planning algorithm computes a path based on linear trajectories and subturns to pick up the object, transfer it, and return to the starting point. In the XARM programming, we accomplish this by utilizing Blockchain, programming for the XARM and ROS for overall system integration. Blockchain provides a user-friendly interface for controlling the arm, making it easier for non-programmers to work with it. In this case, the routine was simple, carried out within the block environment, then transferred into lines of code that will later be used within our program through functions in the coordinates needed.
To execute this project, we use ROS as the backbone of our system. ROS allows us to seamlessly integrate the mobile robot and the XARM. We develop a program that receives the position data from the robot and sends the velocity calculate with control equations to the robot to arrive at desired points. Likewise, we develop an XARM program that contains the routines of pick and place, and furthermore, the conditions to activate this.
Now, let's analyze the behavior of both robots. What we expect is that the mobile robot will display excellent navigational capabilities, quick and agile and smoothly move across the space. And for the XARM, we expect the precise and delicate movements essential for object manipulation. In contrast with the reality, this was so close compared with the simulation. We basically saw almost the same behavior in real life, but with accumulated error. When we say error, we refer to missing calibration of the tolerances using odometry limitations, but the minimum velocities and the inertia present in the real robot.
Talking about the positive and negative points of the program, the main advantage of the program is that it's efficient and precise with the correct calibration. It works with set points that we determine before the simulation. And having made this advantage, it is that a controller requires a lot of data processing. It requires to be constantly communication handled due to the odometry and requires a lot of calculations to achieve the set points. We also had to calibrate the tolerance of the odometry. We face challenge in terms of the complexity of the control system, fine-tuning the arm movements, and ensuring collision-free paths where demanding tasks were assigned. We also encountered occasional errors that required debugging. In conclusion, our project showcases the potential of integrating mobile robots with robotics arms and the power of ROS. This project required a lot of time and patience to adapt the robot programming of the simulation to the reality. We globalized the main points in debugging and physical calibration of the error in the odometry. In debugging, the challenge was to make sure that integration of the points were read correctly and the communication was implemented in the correct way. And in the physical calibration, the hard thing to do were the experiments to know how much distance does it can achieve and check its difference taking into account the established set point to do an increase or decrease of the given set point.